Welcome back. We're going to continue in chapter 8 here. We're going to actually get into creating confidence intervals today. Last time we talked about the basic idea of them, and now we're going to get into actually creating them. So I left off last video with the recipe. And this is the recipe of things you should be following when creating a confidence interval. It is also expected by the AP College Board, so that's why we're going to consistently do this. Now, let's just talk through some of these pieces. We'll break down why we do a couple of things we do, and then we're going to actually do one or two of these confidence intervals. All right? So, step one is to define the parameter. We actually need to define what it is that we're trying to estimate. And in this case, for today, since we're dealing with proportions, we are going to define the parameter as P equals the true proportion of fill in the blank with context. Now we also want to be able to name the interval, and for today it's just going to be these things called one proportion z intervals. And there are different types of confidence intervals that we'll get into later on, but we're just dealing with one proportions, and these are z intervals. We're going to work with the normal curve probabilities from that because we can. Check the conditions. We have to check conditions every time. These conditions are going to be the same, but slightly different depending on the type of interval. So for one proportion z intervals, we need to check, number one, is it a random sample? Number two, is it approximately normal? So large counts conditions, n times p hat greater than or equal to 10, n times q hat greater than or equal to 10. We want to assume that we are working in a normal, approximately normal distribution. And then step number three, is n less than or equal to 10%? Again, with simple random samples, 10% of the population. We can't assume independence, but we can check, and as long as it meets this condition, it will work like it's independent. Our formula. Once we have met the conditions, we can go into actually creating this confidence interval. Our formula is always going to be whatever your point estimate is. In this case, it is p hat. When we deal with means, it'll be x bar. But it is p hat plus or minus z star. That is our critical value, which we talked about last time, how to find those. It's the z-score that kind of bounds whatever percent in the middle of our normal curve. And then it's times the standard error. In this case, it is the square root of p hat q hat divided by n. Step 5, plug the numbers in, crunch your values, and create your interval in step 6. Typically your interval, I will write it like blank, less than, is less than p, because p is what we're trying to estimate, which is less than blank. That's the lower and upper bounds of our interval. You could also do it as our two bounds, our lower and upper bound in that interval notation. And finally, it is very important to interpret, give context to what we're doing. If you want to write this down, this thing I have in the blue box is a good way to interpret it. It's not the only way, but the things that you need are the confidence level, the context, and the actual interval itself. And this provides that in a pretty concise way. So at the blank confidence level, I believe that the true proportion of blank, and if it has to do with people, we can say who blank, is between this and this. Now, with these parts, I want to just talk briefly about the conditions that must be met. And once I have that, then we're going to do a confidence interval or two. So, those conditions. So we have our formula off to the left. Why do we have to have the random sample condition met? What does that have to do? And really, that has to do with the p hat. Okay? Because if it's not random, then we can't actually generalize to the population. We can't use something that's going to generalize to the population. So this allows us to generalize. If you remember back to our unit on sampling, it allows us to generalize to the greater population. And we can actually estimate something. I want to also make note, it makes sure that p hat is an unbiased estimator of p. Also, this all just has to do with good methodology. There's so many people out there who use bad methodology. We don't want to be those people. We want to use good methodology. All right, condition number 2, the large counts condition. So the large counts condition has to do with this guy right here. Remember n times p, in this case we'll use p hat, greater than or equal to 10, and n times q hat, greater than or equal to 10. Those two things allow us to assume approximately normal distribution. And if we have an approximately normal distribution, that allows us to use z-values. And that's why, if we're using a z-score, a z-interval, we have to be able to use that. So that is an essential condition to be met. The third condition, the 10% condition, that goes along with the standard error, the standard deviation of the sampling distribution of proportions. And it is essential because if we don't have it, we can't actually use this formula, and we can't use it. Well, we can use it, it just might not be accurate. So n has to be less than or equal to 10% of the population in order to assume independence. Because otherwise, in a sampling distribution, in a sample, there's not replacement. So we can't assume independence otherwise. All right, let's try creating a confidence interval. The example we have before us says, using a database of all members of the American Medical Association, a research firm generated names of 77 doctors and asked them, that didn't work. There we go. And asked them to name the exercise they thought was best for adults. 56 said that they thought swimming was the best exercise. Find the 99% confidence interval of the true proportion of who believe that the swimming is the best exercise for adults. Okay? Now, we want to walk through those steps, those parts to the recipe for a confidence interval, and make sure we're covering all parts. One thing I want to make note is, I'm going to start off because it doesn't say the proportion, it just says 56 out of 77. So p hat is 56 out of 77. If you want to abbreviate and write that as a decimal, you certainly can. It ends up being about 0.7272. We are also going to be getting to q hat, so that would be the everything else. That would be that 21 out of 77, or everything else. Okay, so something worth noting. One other thing worth noting, we want a 99% confidence interval. You can always use inverse norm for that, but we want 99% to fall in the middle. And the question is, what are these z-scores that would bound that? So you can take inverse norm, and if you have the center feature, you can put 99% in the center. Or you can just put what would be in the ends would be 0.5%. So you can put 0.005 in there, and it'll just give you everything to the left of whatever your z-value is. You end up getting a z-value of 2.576. If you use your formula, or sorry, your z-table, you can get it to 2.58, and that would be just fine. Now, let's go through the steps. Step 1. List the parameter. Define the parameter. So P, we're looking at a proportion, is the true proportion of, we'll say, American Medical Association doctors who believe swimming is the best exercise. For adults. Now, we want to check the conditions. We also want to get into what this is that we're doing. So we are going to be doing we'll say step 2 is here, step 3 is here. Because we have to get into the conditions. But before we do the conditions, we can also list, doesn't really matter the order here, list your type of interval. This is going to be a 1 proportion Z interval. All right? Before we do any work with that, though, let's go into the conditions. Condition 1, is it a random sample? It is. It is a random sample of 77 AMA doctors. So we'll say it's stated. Second one, is it approximately normal? Can we check the large counts conditions? So if we have 77, n times p would be 77 times the 56 out of 77. And is that greater than or equal to 10? Yes. And is 77 times the other one, 21 out of 77, q hat, greater than or equal to 10? Yes. So we can say both yes here. So we will proceed. And the last condition that needs to be met is the 10% rule for independence. Is 77 less than 10%? Of all doctors? I know it's the AMA doctors, but I think most are in the AMA. And we're going to assume yes. Which means all our conditions met. So we can go on to step 4. What formula are we going to use for this? Well, that is our p hat plus or minus our z star, which we already found, times the square root of p hat, q hat, over n. And let's actually plug in and get our interval. All right. So 56 over 77 plus or minus. We said that z star was 2.576 times the square root of, yeah, I'm going to put this in there as it is, 56 out of 77. You can use the decimal if you want, but that would be rounding, so I don't want to round yet. Our n was 77. So that gives us about 0.7272 plus or minus 0.1307. And I can take that information and actually write the interval. So the actual interval, which is technically step 6, would be P is between 0.5965 and 0.8579. There is our confidence interval. The last step is just to interpret that. So I can then say at this 99% confidence level, I believe that the true proportion, which is what we're actually trying to estimate, of doctors believe swimming is the best is going to be between 59.65% and 85.79%. There we go. That is our confidence interval. So I'm going to give you a second one. I'm going to say to pause it and try it. This one is a 95%, which is a common amount or common value. A random sample of 500 college students in Wisconsin was asked whether they skipped breakfast. 214 said they did. Find the 95% confidence interval of the true proportion. So I'm just going to say pause it and try it. I'll show you what I got, but this is a little bit different. It's one to try on your own, and it's a different confidence level. All right, here's what I got. I got my p-value, so true proportion of Wisconsin college students who skip breakfast. It's a one proportion z-interval. Check the random sample. We checked the large counts conditions, and we checked the 10% condition, and yes, they all check out. Well, we're on the right there. We've got our formula. We've got it plugged in for the formula, and we've got it reduced. That gives us an interval from 385 to 0.471, and I can interpret saying at the 95% confidence level, I believe that the true proportion of Wisconsin college students skipping breakfast is between 38.5% and 47.1%. Okay? Now, last thing I want to touch on is a question. It says Mrs. King placed a survey in every Hamilton High School teacher's mailbox. There's approximately 100. They were asked to choose their favorite fast food restaurant among Domino's, Little Caesars, Pizza Hut, Papa John's, or Mod Pizza. Of the 66 respondents, 27 named Mod Pizza as their favorite. Address the assumptions. Now that's dealing with the conditions that have to be met in order to do this. And in this case, first of all, it doesn't say it's a random sample. It was just put into the mailbox and take what we get. It does meet the large counts condition, but it doesn't meet the 10% condition because 66 isn't less than 10% of 100 teachers. So that's two conditions that aren't met. This is poor methodology, and we shouldn't be using, we should be creating a confidence interval based off of this. So not all conditions are always met, but I want to show an example of when that happens. All right? But that wraps it up for today on day one of confidence intervals. I'll probably add a second video similar to this, maybe just reviewing those steps and then going into a couple of different things we can conclude about them. But ultimately, this gives us an idea of how to set up and create a confidence interval for proportions. And that's section A2A. We'll see you next time.